Section 4.2 is on page 276. So I claim the purpose of chapter 4 is mainly to sketch a graph of polynomials. We're going to spend enough time on this. I'm going to go way more in depth than the book does, and we want to make sure that we master this idea. So on page 276 it says polynomial functions and their graphs. So in 4.2 we're given the factored polynomials, we're going to graph them. In the remaining of the chapter we're going to factor the polynomials so that we can graph them. So this is a crucial section. A polynomial f of x equal a sub n x to the n plus a sub n minus 1 x to the n minus 1 all the way a sub 1 x sub 1 plus a sub 0, in which n is a whole number. That means n could be 0, 1, 2, 3, no fractions, no decimals, and no negative numbers. And a's, these are just the coefficients. So if I'm dealing with a quadratic, I just need 3 letters because there are only at most 3 terms. I just need a, b, and c. But if I have x to the 20th power or x to the 200th power, I don't have enough letters. So instead I could write this as a sub 2 x sub 2 plus a sub 1 x sub 1 plus a sub 0 equal f of x, and relating what those are to those. Nothing more than the a, b, c, the numbers. It turns out a key to this whole set is the leading term. A key to this entire graphing business is the leading term. End behavior of a polynomial as x grows very large or very small, either reach to the right infinity or negative infinity, is determined by the leading term. So this term is going to determine a lot of things for us, and without the leading term and studying that, we can't sketch a graph. So we have the power, we said, is a whole number. So n could be even or n could be odd, since it can be decimals or fractions. If the leading coefficient, that's what a sub n is. A sub n is called the leading coefficient. If the leading coefficient is positive, think of this. Anytime I look at even, I'm thinking of y equal x squared. If the number in front of the square is positive, the end behavior mean when I look at the far right and the far left, the graph looks like a parabola. And if this leading coefficient is negative, then the parabola is going to open downwards. If I see that power being odd, then I'm thinking of y equal x cubed. If the coefficient, the leading coefficient, is positive, then y equal x cubed looks something like this. And y equal negative x cubed, if the leading coefficient is negative, those will switch and look like that. This is called end behavior. And what that means, we're only looking at the far right and left. We're not looking at the inside of this. That's the hard part. And I'll show you how that works. This section really answers all of these questions. So they're saying, describe the end behavior of the graph. You really don't have to put a sketch. I am going to do a rough sketch just so that we really see it. Describe the end behavior. Well, look for the leading term. What's the highest term? Is it, oops, almost messed up. Isn't this the highest term? The leading coefficient is x cubed and it's positive. That means it's going to look toward the very end. So we know y equal x cubed looks like this. We're just going to take the endpoints. Something like this. So, if n is odd, if n is 1, 3, 5, 7, n is even 2, 4, 6, 8, the graphs will behave just like this. Meaning, if I look at number 4, I notice the leading term is negative 5x to the 4th. to the 6. So again, if n is even, I'm thinking of a parabola. Since this number is negative, the parabola is going to open down. The end behaviors are going to look like this. Here, I notice that the highest power term, the leading term, is 7x to the 8. X to the 8 even, like x squared. Since that's positive, that's going to look like a parabola in the long run. There it is. Now, they ask us to graph, and we know how to graph those, but I want to really elaborate on something you have not paid attention to yet. And let's do that. So, if I look at y equal x minus 2 to the 5th plus 3, I know this is a 0. If I set that equal to 0, that's going to be 0 at 2. And up 3 units, 1, 2, 3. Here we go. X to the 5th, x to the 3rd, x to the 7th looks like a cubic. Now do keep in mind, this is a rough sketch. If I put 0 in for x, I'll get negative 2 to the 5th, negative 32. Negative 2, 4, 8, 16, 32. Plus 3 is negative 29. This point is negative 29. And I don't have to worry much about the scaling the y because there's only one point that comes up since this is a function. If I look at number 10, I know what x to the 6th look like. That's a parabola. Negative means it opens down, and this is going to shift it 3 units down. 1, 2, 3. So the graph looks something like this. Now, what do you suppose happens if I have the 5th and the 6th in one problem? Well, let's see how this works. Where does x equal 0? At 0 and at 2. So I'm going to start with the end behavior. If I multiply those out, wouldn't the leading term be negative x to the 6th times x to the 5th? That's negative x to the 11th. If the power is odd and it's negative, doesn't that look like this? End behavior. A graph must cross through intercepts. So initially I was going to do this. I was going to say it looks like this. And it's right here. But since the graph must cross the intercepts, well, it's going to cross this intercept and it's going to run through that intercept. Now, something that we didn't pay attention to is multiplicity. Not to worry if I'm saying a lot of times you're not understanding. I'm going to do more than enough examples and say these terms over and over until we get it. So the goal is to make you sick of this today. And getting sick of something in math is a good thing. Do you notice that x to the 6 is right there at 0? That means that graph must look like x to the 6 around that 0. And do we see that x equal 2, you have a power of 5? That's called multiplicity. That means what? It's going to look like a 5th degree, but the graph is already made. That's why I need the end behaviors. So it's either like this or the other way around. And I need to make it looking like that on the right hand side. So I need to adjust that graph and make it look like a cubic. And that's how the graph looks like. If you didn't get this example, that's okay. Again, I'm going to do a bunch of those. I'm doing about 3, 6, 9, 12, 15, 20 graphs before I even get to the book. So let me get this out of the way completely. And let's make sure we understand this solid. Because I'm going to assume that you know how to graph anything I throw at you after this. You have 12 homework problems to do. I'm doing 34 examples. Hopefully you're not going to underestimate this. because you must master this. If I look at such a graph, first I need the zeros. This equals 0 at -2. And this equals 0 at 3. You know what? I need to rescale this. This equals 0 at -2. This equals 0 at 3. Something that I should get out of the way. I should do this all the time. If x equals 0, that's very easy to find. Put 0 for x, you get 2 times -3, -6. I'm going to assume this is -6. Doesn't this behave like x squared? If I multiply this out, the leading term is x squared. And I'm going to run down. And do you see the power is 1 on each of those? That's like y equal x, so it's a straight line sort of. And that's a graph right there. What if I square one of those? What would happen? Well, I'll notice x equals 0 is still at -2. That didn't change. X equals 0 at 3, 1, 2, 3. Those are the zeros. If I put in 0 for x, I'll get 2 squared, which is 4 times -3. That's -12. I'm going to label this point as -12. Again, the graph is not to scale, but I could scale the y-axis anywhere I want. If I multiply this out, doesn't this behave like x cubed? Positive x cubed? Isn't positive x cubed gonna look like this? Well, the graph has to pass through its intercepts, so instead of just putting those there, I know that the graph has to go through the intercepts, so it has to look something like this. Now comes the tricky part. Left to right, I'm gonna do every graph. Do you notice that this is 0 right there, but it has a power of 2? That means that has to look like a parabola. How can you make this look like a parabola around -2 specifically? Don't you have to come back down to make it look like a parabola right there? Now, the one thing you can't figure out whether it opens up or down, that's beyond the... That's why we do end behavior first. The graph must cross through its intercept. And do you see that this is 0 right there, but the power is 1? That's like y equal x. Y equal x is a straight line. So around that 0, it's like a straight line, and then you curve it afterwards. And there it is. If I look at the next problem, x equals 0 at -2, x equals 0 at 3. So basically, I'm taking on all different combinations. If I put 0 in for x, I'll get a 2 times -3 squared. That's 18. 9 times 2 is 18. I'm going to say this is 18. Now, if I multiply this out, doesn't this behave like x cubed? And I already know the drill. X cubed look like this, but since the graph must pass through its intercepts, the graph really looks like this. Now comes left to right. This is 0 right there. But do you see now the power changed to 1? That's called multiplicity of 1. That means this is going to behave around the 0 like y equal x. Y equal x is a straight line. So a straight line right there. And do we agree that this is 0 right there? Isn't that a square? That means the graph must look like a parabola around that 0. Continue this with a smooth curve. There's the graph. So, it is impossible for this to be a 2 and this not to look like a parabola. There's no way that could happen. What if I square both? Well, what if you square both? Let's take, where are the zeros? This is 0 at -2, -1, -2. This is 0 at 3, 1, 2, 3. The y-intercept, if I put 0 in there, 2 squared is 4, -3 squared is 9, that's 36. I'm going to say this is 36. Doesn't this behave like x to the 4th, positive x to the 4th? doesn't that mean the end behavior, they have to go through those intercepts, so they're gonna look something like this. Left to right. This is 0 right there. Since that's a 2, around that 0, I have to force that to look like a parabola. And this is 0 right there at 3. It's a 2. I have to force that around 0 to look like a parabola. And if I continue this with a smooth curve, there it is. This is not an exact graph, but this is as accurate as we want to get. And I want to tackle in this video 3 more graphs. Highlight 5 more graphs. And the next video I'm going to add another 0 to make this more fun. So I want to do one more after that. This right here, and then we'll conclude this video and we'll continue the rest in the next video. So 5 graphs. Let's see how long that's going to take. This right here, this is 0. Oh, I didn't center any of those. Oh, okay, that didn't register at all. I get when that happens. Okay, so let me move this just a bit. Here we go. Gotcha. Okay, so this is 0 at -2, at -1, -2. This is 0 at 3, 1, 2, 3. If I put in 0 for x, I will get 2 cubed, which is 8 times -3, -24. I'm going to say that's -24 right there. If I multiply this out, x cubed times x is x to the 4th. That's going to behave like x squared, so to speak. Now, do we agree that this 0 is right there? It's a cubic. So I really need to make it look like a cubic. If the right side is opening upwards, so to make it a cubic, we're really going to come down and make it look like a cubic. It's going to hit that. And do you see that here? The 0 on this is 3, but the power is 1. So around this, it's going to look like a straight line. And just a smooth curve will do. Okay, this example now again. This is 0 at -2, -1, -2. This is 0 at 3, 1, 2, 3. The y-intercept is 0. 2 times -27 is -54. I'm going to say that's -54. And if I multiply those out, that's like x to the 4th. X to the 4th behaves like this. Left to right, this 0 is right there. And since the power, the multiplicity is 1, it's going to look like a straight line. So kind of a straight line there. It's going to come down. And this is 0 right there. The multiplicity is 3. I need to make that look like a cube. Well, a cube looks something like this, wouldn't it? Because I know the right end behavior has to go up. And connect this any way you like and you're set. On this problem, this 0 is at -2. This 0 is at 3. If I put in 0 for x, I'll get 2 squared, which is 4 times -27. I don't know what that is. I could figure it out, but I really don't care. I'm just going to mark that somewhere right there. And I have it listed right there, so I know what that is. This is going to behave like x squared times x cubed. That's really like x to the 5th. X to the 5th indicates like it's a cubic. Left to right, this 0 is right there. It looks like a parabola. Well, if I know this is going to come down, to make it look like a parabola, it has to come back down, right? And this 0 is right there. It's a cubic, so I need to make it look like a cubic. A cubic, since this is going to open up, a cubic will look something like this. And that'll do the trick. So without end behavior, there's no way of telling which way the graph will open up. Here, we have a 0 at -2, -1, -2. 3, 1, 2, 3. If I put 0 in there, I'll get 8 times 9, 72. I'm going to assume 72 is right there. This behaves like x to the 5th. That's what x to the 5th look like. Left to right, this is 0 right there, but it's a cubic. The multiplicity is 3. So a cubic looks like this. That takes care of this. It has to pass through that point. Remember, 72 is way up there, right? So if I mark 72 right there, the graph looks a lot smoother. It should be a smooth graph. So this is a cubic. Now, on this 0 is right there at 3. It's a square. Since I know it's going to open up, then I know it's going to look like a parabola, so I have to go back up and connect it, and there's the graph. And if I look at the following example, the 0 is at -2, the 0 is at 3. If I put 0 in, I'll get 8 times -27, right? Which is negative, you know what, minus, well, 56, 16, 21, -216. I'm going to say -216 is right there. If you multiply those out, this is x cubed times x cubed. That's like x to the 6th, like a parabola. Left to right, this 0 is right there, but that's multiplicity 3. And since I know it's going to open up, I'm going to make it like a cubic. And that takes care of the end behavior. That's why the end behavior is very important. It's going to go through that intercept. Okay. And this 0 is right there, but that's cubic as well. Since I know it's going to open to the right that way, I know that this is going to be a cubic, but opening this way. So there it is. And connect them here any way you like. We're not going to disagree on that. And there's the graph. So I'm going to stop here for this video. The next video, I'm going to do 3 intersections and deal with all of these cases.